For over a century, theoretical physics has pursued a singular ambition: a complete, consistent, and unified axiomatic framework that flawlessly describes all fundamental forces. To qualify as a true theory of everything, this framework must accomplish a specific mathematical feat. It must consistently combine the quantum field theories of the Standard Model with Einstein's general relativity. Preserving diffeomorphism invariance is a core requirement of this integration. In general relativity, space-time points have no absolute meaning independent of the dynamic degrees of freedom representing geometry and matter fields. Analytical. This entire quest relies on the assumption of strict ontological reductionism. This philosophy posits that all macroscopic reality supervenes exclusively on a microscopic foundation, implying that knowing the lowest level rules allows for the derivation of all other phenomena. Under this model, a final theory must leave zero empirical content unexplained. It is tasked with accounting for dark matter and dark energy using the exact same finite set of rules as the Standard Model. Strict ontological reductionism makes the pursuit of a theory of everything the single, absolute path toward a mathematically complete science. But the foundation of this pursuit cracked when mathematics collided with physics. In the mid-20th century, Kurt Gödel introduced formal undecidability, proving that sufficiently complex logical systems contain statements that can neither be proved nor disproved. Recent applications of these mathematical impossibility theorems demonstrate that a final theory of everything is structurally unachievable. This limitation stems from hard limits built directly into the structure of formal logic, rather than a lack of experimental data or human intelligence. Confronting this mathematical wall forces theoretical physics into a difficult position. The discipline must either accept a permanent ignorabimus, the decree that we will not know, or it must reconsider its foundational reductionist philosophy. Acknowledging the formal limits of a theory of everything exposes a structural flaw in reductionist philosophy, shifting the focus towards scale-independent behavior. To identify exactly how mathematics breaks the final theory, we must examine the most extreme concentrations of physical information in the universe. Chaitin's algorithmic complexity establishes that formal systems have strict limits on the statements they prove. A mathematical axiom system is a finite string of information. Applied to reality, describing a black hole's massive informational density requires generating a data string of immense length. If the informational density inside a black hole requires more bits to describe than the axiom system contains, the math becomes silent. The physical complexity of the environment exceeds the proof-generating capacity of any putatively final set of axioms. Any mathematical system tasked with describing environments denser than its own algorithmic limit will inevitably contain unprovable statements. This ensures that a theory cannot compute the entire universe. The impossibility compounds when we look at the foundational geometry of the universe. Current unified candidates, such as string theory, rely on modeling spacetime as a smooth, continuous manifold. Mapping physical spacetime to a mathematical continuum introduces Cantor's undecidable infinities into fundamental physics. This invokes the continuum hypothesis, which remains a statement that standard set theory can neither prove nor disprove. The spectral gap separates a quantum system's ground state from its first excited state. When calculating the universe's wave function, the assumption of continuous spacetime disrupts computation. The continuum's infinite variables make it mathematically undecidable to prove if this gap exists. Unless spacetime is fundamentally discrete, composed of finite units, the question of whether two quantum states are macroscopically distinguishable becomes uncomputable. Because continuous spacetime relies on unprovable mathematical infinities, researchers cannot definitively calculate the energetic foundation of quantum gravity. There is a deeper blind spot in the reductionist model. A truly universal theory must mathematically account for the physicist observing the universe. In formal logic, self-reference is notoriously problematic. As demonstrated by Russell's paradox, logical systems reach an unresolvable contradiction when they attempt to define themselves using their own rules. A human observer is composed of the same atoms and governed by the same physical rules they are attempting to describe. A physicist writing the final rules of those atoms is attempting to formulate a complete description of the system that includes the description itself. Translated into physical topology, this means there is no outside vantage point. The universe cannot compute its own inside because the observer is embedded in the geometry they are trying to measure. Observations actively determine the outcome of quantum processes. The observer's deciding faculty contributes directly to the creation of physical reality, making it an inseparable part of the universal subject matter. A universe trying to compute itself from within enters an infinite loop, resisting axiomatic closure. If the mathematics of a final theory are broken by algorithmic complexity, the continuum, and self-reference, physics must find another way to function. Tarski's undefinability theorem states that a putatively final theory cannot define its own concept of truth. Mathematically, absolute formal truth within such a system is unreachable, but the physicist operates under a different standard. Physics does not require a generalized definition of absolute mathematical truth. It requires the results of specific computations, which are then tested against finite observations. The discipline is driven by results that can be verified by experiments, such as those measured inside the ATLAS detector at CERN. If the computation describes what we observe, the model holds. Physics survives the mathematical death of the theory of everything because its ultimate master is finite empirical observation, not the infinite demands of formal logic. The anxiety over losing a single bottom-up foundation only exists if we assume the macroscopic world strictly supervenes on the microscopic world. This diagram shows renormalization group flow. It maps how physical systems change behavior at different distance scales, tracing physics from high-energy microscopic points down to low-energy macroscopic environments. Mathematical analysis reveals that, except at specific fixed points, this flow between scales is reversible. The large scale mathematically dictates the behavior of the small scale just as effectively. If the flow of information between scales is symmetric, the macroscopic world does not unilaterally supervene on the microscopic world. This scale symmetry removes the need for a bottom-up axiom. Fundamental reality operates as a bidirectional web of influence. The quest for a theory of everything failed to account for the universe's inherent self-reference and the unprovable variables of a continuous spacetime. These limits allow for a non-reductionist approach, where physical theories remain valid at their specific scales of observation. They do not need to reduce to a single point to be considered complete. The search for understanding remains an open process, ensuring that physics continues as a creative exploration. The formal impossibility of a single theory reveals a universe with a topology far too rich and self-referential to be contained by a finite set of rules.